And the first chapter of this morning session is by Rowan Smith on initial conditions for star formation, a physical description of the filamentary interstellar medium. Okay, so please start.
Thank you very much. Good morning, everyone. It's lovely to see you here. And it is fantastic to be able to join you to share the results of Chapter 5, where we've been looking at the filamentary interstellar medium, which of course gives us the initial conditions for star formation. Now, I represent here my whole team, who you can see on the screen here. We have our glorious leader, Alvaro Hacar, but also Fabian Heitsch, Daniel Seifried, Susan Clark, Gina Panopoulou, and Jouni Kainulainen. And this is our faces when we finally finished our PP7 review. And as you can see, only Daniel knows how to celebrate properly. The rest of us are wussies. But for this review, we decided to take a slightly different approach. Rather than doing just a narrative summary of the extensive literature on filaments, we decided to use data. So what I'm going to present to you today is the results of a meta-analysis where we have tried to synthesize the results of the field over really the last decade to draw some general conclusions. And in case you're feeling a little bit sleepy, here are the results right now, just to keep you awake. So I'm going to show you that the interstellar medium is threaded with a network of filamentary structure. I'm going to show that this is a continuous hierarchy of nested substructure that connects from large scales down to small. These filaments obey common scaling relations, are formed by many processes, are dynamic objects that constantly evolve, and are intimately connected with how stars and planets form. So when we were bringing together the data, we synthesized several kind of observational filament families because this last decade has been a golden era for the observations of filaments. Ever since Herschel revolutionized our understanding, we have seen these structures on a variety of scales. So the families we've roughly grouped them into are, first of all, the giant filaments, the largest and most massive structures in the Milky Way on scales of hundreds of parsecs, and associated in many cases with galactic structure such as spiral arms. Then the objects found from galactic plane surveys, such galactic filaments and infrared dark clouds. For example, the majority of the Atlas Gal emission is all in filamentary structures. Moving closer to the structures which we can see more clearly, in nearby filaments, we see that these contain networks of filamentary structure. This is a small fraction of the area, but it dominates the mass budget. Looking at this substructure, in places we see it takes the form of hubs, where you'll have multiple filaments extending out from a roughly parsec-sized clump. And this is clearly associated with massive star formation. Going down to yet smaller scales, below a parsec, we see the fibers. These are velocity-coherent subfilaments, which are identified in ppv space, the smallest scale of our hierarchy. But it's not just in the dense gas. We also see diffuse structures, striations, which are elongated perpendicular to the spine and periodically spaced parallel to magnetic fields. And it's not just in the molecular gas. We also see such structure in the atomic. For the diffuse medium, we can see slender H1 filaments which pattern the sky and are aligned with the plane of sky magnetic field. And just recently, we've also seen that there are massive structures as well. These huge extended H1 structures of up to a kiloparsec, possibly more, reminiscent of the giant filaments. And so from this dichotomy, you can see that filaments are everywhere in the interstellar medium. So let's collect this data together now for our meta-analysis. So this is a huge community effort. I've put just some of the references here on the right-hand side of the screen. A lot of this data came from papers which are published in the literature. Some of it came from within our team, but we also want to give thanks to these authors at the bottom here who directly share data with us. We're very grateful. So in total, there are over 49 observational works included, almost 23,000 filaments, which of course is enough that one can do statistics. There are some qualifications. This is an inhomogeneous sample. We have certain objects multiple times. Everyone loves to observe Orion, for example. It's also incomplete. In terms of velocities, we don't have those for all the structures. And for the magnetic fields, we really do only have a few measurements. So we are more limited in the conclusions we can draw there. But in terms of the positions and lengths, we have that for just about the entire sample. So this is the result. These are all the molecular filaments which you can see in the Milky Way. So at the top, we have the giant filaments, right down through the galactic filaments we see in surveys to nearby molecular clouds, and on the smaller scales, these fibers. A couple of points you can see from this point. All the families join into each other. As I said, these are kind of loose categorizations. There's no clear, obvious physical distinction between them. They join into each other. The other major point is you can see that there is this common scaling relation across multiple orders of magnitude, from scales of 0.1 parsec to 100 parsec. They all follow this same scaling relation, that the length is proportional to mass to the power of a half. So we can think about this in terms of the filament stability. We know that for a hydrostatic isothermal cylinder, we characterize that in terms of a line mass. And this is a well-known classical result since the days of Sadowskis and Oestreicher, which I mangled the first name of. But we have a relation for the critical line mass, which can be supported against gravity by thermal support. And that is this line here. As you can see, it in no way follows the data. Instead, if we try and include an additional form of support, we can see that there are non-thermal motions in these filaments. There is additional turbulent motions within the structures. We can include that turbulence support, and we get this relation here, which gives us the scaling shown by the red line, which follows the trends of the data much better. So, does that mean that these are hydrostatic objects? Well, probably not. Let's look in a bit more detail at the velocity dispersions that we observe. So here's our full filament samples again. On the smallest scale, you can see the fibers with the sonic velocity dispersion. And then as you go up the scales, the velocity dispersion increases to the power of length to the half, with the most massive giant filaments being highly supersonic. It's not just a relation with mass, with length, it's also to do with the line mass. So if we look here, we can also see that as the line mass increases, so does the observed velocity dispersion. So is this velocity dispersion acting as a uniform pressure support? Well, there is a big problem. And that's because when you look at the largest structures here, while the distant ones are completely unresolved, when you see closer, you can see that there is hierarchical substructure within them. So let's take Orion as an example. If we look in this diagram here, in blue, you can see the points of Orion. This is the entire filament. This is smaller filaments seen within it, and these are the fibers. And you see, these all lie at various points along our mass to length scaling relation. And so what appears to be thermally supercritical on the largest scale resolves itself into individual transonic structures on the smallest scales. And so, once upon a time there was a philosopher, and he was asked, how do you support the Earth? And he said, well, it's very simple. It's on the back of a turtle. And then he was asked, well, what keeps the turtle up? Ah, he said, it is turtles all the way down. Now, I'm not sure if that's true of turtles, but it certainly seems to be true of filaments. It seems to be filaments all the way down. Everywhere you look, it resolves into smaller structures within structures, and we do have this hierarchy. And so, what does a line mass mean in this context? Are we talking about the largest structure? Are we talking about the smaller ones inside it? This is not acting as a smooth, continuous filament. There's another scaling relationship that we see here, and that's to do with the density and the length. That as you go down to these small scales, the density increases. So there is an inverse relation between the length of the structure and its density. One other point to make here before I move on. We can see there are some points which clearly depart from this relation. These are the hubs associated with massive star formation and the ridges, which are very similar. And so they clearly are objects which are a little bit different. Another thing which we can characterize for these filament structures is their radial profile. Again, we can draw on the insights from the idealized model, looking at an isothermal Oestreicher filament. So these can be characterized by plumber-type radial profiles in terms of the intrinsic 3D density and also in the column density. And for this idealized case, you would expect an exponent of about 4. So quite a steep fall off, and a flattening radius which scales with the local thermal state of the gas and the central density. But that's not what we observe. So observed filaments in Herschel, and now quite a broad of other sources, have shown that you have an exponent of between 1.5 to 2.5. Think, what could be causing this departure from the isothermal case? So we've looked at various different physical forces to see how this can affect the width. And the unfortunate thing is that whatever you look at, it flattens the profile. If you include magnetic fields, it flattens the profile. If you include external pressure, it flattens the profile. If you include non-isothermal gas temperatures, it also flattens the profile. So unfortunately, you can't say there's a single cause for this. You do expect variation with these processes, so you would expect that for there to be an inverse relationship between the full width half maximum and the external pressure. So if you squeeze the gas more, you have a narrower filament. But this is just not observed. In fact, the whole issue of widths can be a bit contentious. So in the Herschel data set, it was found that there was a narrow distribution of widths in nearby clouds of about 0.1 parsec. But as I just said, theoretically, you would expect this quantity to vary. And when you look at the broader data set as a whole, there isn't a constant value. So if we look to the different filament families, clearly the giant filaments are not 0.1 parsec across. This is not always seen in all tracers. For example, observations in gas tracers, dense gas tracers, maybe show you something narrower. Something in CO, which is tracing more the envelope, is a bit wider. And when you look at individual filaments, you can get variation along their length in their width. So one thing which we did as part of this exercise was look at some of the Herschel data with updated distance estimates from Gaia. When you do that, there is actually a bit of a linear correlation between the length and the width. There's also a correlation between the average full width half maximum and the distance which you observe the structure at, which you can debate the origin. It could be resolution, it could be something else, it could be how you calculate the width given the shape of the profile. But there does seem to be this dependence And indeed, the entire concept of width, when you come to these more massive structures, is a bit hard to define. If we're talking about a superposition, something which is made up of many different structures, then that is not a smooth cylinder. How do we define the concept of a width for those objects? Now, moving on, something which is very important for filaments is magnetic fields. And when we did this meta-analysis, there actually wasn't that many measurements available in terms of the field strength. I'm pleased to say over the last year, looking at the literature, that is changing. But I think the next chapter will go into this more extensively. So I'm going to leave it for the next talk to look at this area in detail. In terms of the stability, so far we've kind of focused on the stability of the objects, the velocity dispersion. But of course, there is another way in which you can get velocities, and that is along the length of the filament structure. And again, we can draw in our meta-analysis of the field to look at how that varies with length. So this is the data. You can see that for the subfilaments and for the fibers on the smaller scale, you can get quite high velocity dispersions. But once you get to longer lengths, this drops down, and you have longitudinal gradients of only up to 1 kilometre per parsec, or even lower in some cases. And you can see an example of what I mean here. So here's a filamentary structure, and you can see the velocities are going from blue here down to red at the other end of the filament. And so there are flows along these structures. So to summarize, here are the properties which we've derived for our filament families. I put that up just so you can see it. If you want the details, you can look at the review. I think the important thing to stress here is that there are plenty of question marks, and so there is lots of work still to be done for the next protostars and planets. So let's take a bit of a step back now. We have collected the data from all these different structures in the Milky Way. Let's try and take a step back and understand the physical interpretation behind this. So the thing I haven't mentioned so far is, how are these structures formed? Well, if one looks in the scientific literature, you can see a wealth of information about how to form filaments. If you look very classically, simple gravitational collapse will give you filamentary structures. First collapse to a sheet, and then along it into filaments. So here's an example from Miyama et al. In 1987. And this is what gives us the cosmic web, for example, in cosmological works. But we're not like cosmologists, we have gas. So we also have a medium that is extremely turbulent. And so if we look at a network of interacting supersonic turbulent shocks, such as shown in this simulation by Christoph Fedroth, what does that give you? Where you get the shocks, it brings gas together, it compresses it. What do you have? You have a filament. You have a series of these interacting, and that gives you a network of structure, just like we observe. But you can also add magnetic fields to this process. This further encourages the formation of filaments, both because it gives you a preferred direction, which the gas can more easily flow along, but also because it gives you a magnetic tension, meaning that if you shear the gas, it's more likely to stay as one continuous object. It's not just magnetic fields. Feedback also can induce filamentary structure. So if we think the case of supernova, you can sweep up material into shells that break. We can have radiation feedback, pushing the gas together, evaporating the edges of structures, photoevaporation, stretching gas out into streamers. Once again, we have filamentary structure. Going to the largest scales, you can see that galactic structure is also highly filamentary. if you have clouds rotating around the galactic potential. They can be compressed as they fall into spiral arms, which gives you a filament. But then they also just, the act of differential rotation stretches material out, as we saw a nice example of yesterday for the OB associations. So everywhere you look, you see filamentary structure. I will let you into a secret. When we first tried to do this analysis, our idea was that we're going to look at all these different physical mechanisms, and we're going to look at the properties of the filaments, and we're going to try and use them as a tracer of the physics that causes the filament and look for differences. And the sad truth is that when we did this analysis, we just could not separate them in the data. There really was no difference. And so what I personally take from that is much like the movie I watched on the train, on the plane to get to Japan, filament formation is something that happens everywhere, in everything, all at once. And that's why you see it everywhere in the interstellar medium, because all the physics that happen in the interstellar medium lead to filamentary structure. But this filamentary structure, as I just showed, is not in isolation. It's connected to its environment. So let's think about that. So external pressure confinement. If something is pushing a filament together, if that filament is itself unbound, if that pressure confinement moves or changes, then the filament will just dissolve. This can suggest that often these structures, which we put quite a firm line around, could actually be just dynamical, transient filaments on the larger scale. Also, when we look at the most massive filaments, we see that they are embedded in a higher column density material. Now, both simulations and observations, when you look at the environment, what you see is these perpendicular velocity gradients, which can be indicative of accretion onto the structures from the environment. So here is a nice simulation by Shenetol in 2020, and that kind of shows this point. You see the filaments. Look at the simulated velocity gradient. Again, red to blue. There is a flow of material onto these structures. And that could drive turbulence, helping to explain the velocity dispersions that we see in these structures. Though it's important to note that since this flow is inwards, the energy input parts can never be enough to overcome the collapse, just by kind of energy balance. You can't get more out than you put in. And so this is unlikely to be supportive. And looking within the filaments themselves, again, we see that this is a dynamical picture. So on the left here, I've just shown one of my own simulations where I've taken a molecular cloud and I'm stepping through it in density slices. So blue is density, and the arrows show you the velocities. And you can see that while these filamentary structures might be coherent, they are moving. And so it is a coherent structure which is moving with a bulk velocity through the larger filamentary cloud. And we can see that it's a dynamical picture with these structures moving and shifting and interacting with each other. And along the spines of the filamentary structure, there are velocity gradients. So these often take the form of oscillations. If you look at this work here from Daniel Seifried, you can see how mass is channeled along these filamentary structures. And you also, when you look at the velocities, you get almost like a wave-like pattern or something, as is shown by the work of Jouni Henshaw, for example. And sometimes you think, how do we form this? Well, you could form it by accretion onto kinks along the filaments. But another way of getting such velocity observations is say that this is tracing where we have collapse and accretion flows within the filament. And so what's happening is that mass is flowing along the filament onto sites of collapse and accretion. And this provides additional mass to further grow the mass of fragmentation within these structures. And that's the next topic I want to move on to. So we've known for a long time that, going back to our very useful simplified model of the isothermal filament, that hydrostatic filaments filament under gravity if perturbations exceed some critical wavelength with a fasting growing mode, which is about 2 times this value. Nagasawa, 1987. But when we look at more realistic filaments, such as those we see in the interstellar medium, we do see a more complex picture. So while the median fragmentation spacing might be similar to that observed, it is rarely evenly spaced. It's quite unusual to find it. What might be the case is that the spacing of the fragmentation is also hierarchical. So if we look at this simulation from Seamus Clark, you can see that on a small scale we have little cores of fragments separated by the gene scale, and then we have a larger spacing on top of that determined by the gravitationally unstable modes in the larger filament. And so putting together that process of looking at the environment, the accretion, the dynamics of the filaments, we can once again revisit our mass to length relation. Let's try and have an understanding of why it acts the way it does. So first of all, there's this exponent, the scaling, where the length is proportional to mass to the power of a half. Why do we get this scaling? Well, we could think of several reasons, and in the review we didn't really arrive at a final one, we just thought of what some suggestions could be. One thing you could have is random hierarchical fragmentation. If you think of a random walk process, if you were to say what fragmentation was to be something similar to that, you get a scaling of 1 over the square root of n. And if the number is just related to the mass, then that gives you this scaling here. Another possibility is that this is just algorithmic. I've not really had time to discuss in this review how we find filaments, but it is a complex topic, and you can look in the review for more detail in that. Or it could be something with the way that we assign mass to the filaments. Perhaps we could be saying that in the larger structures, we include more of the envelope of the filament into the total mass, whereas for the smaller structures, we only really assign the high density peak. And again, that would be consistent with this idea of hierarchical structure and just accessing a larger spatial scale. What we cannot do is explain this scaling simply by segmentation. If you have a filament that has a constant mass to length ratio along its length, and you just chop that up, well, each part would still have the same mass to length scaling, and you would get this steeper relation. So there has to be something else going on here. Another approach to explaining this diagram is to think about the upper and lower limits. So there is quite a sharp transition between the H1 filaments, in this case we're only including the diffuse H1 structures, and the molecular filaments. And that makes a lot of sense. We did an estimate of what the column density shielding would be for our filament meta-analysis sample to protect it against the UV. So we came up with this relation here, which is shown by the dotted red line. So anything with a column density more diffuse than this is unable to shield molecular hydrogen from the ambient UV field, and therefore the gas will be dissociated. And this fits the data very well. And so it's almost as if you can get filaments which can be as diffuse as you like until you hit this threshold. And then obviously the molecular gas can no longer survive, and we get them dissociated to form H1. And so that might set the upper bound to our distribution. On the lower side, we have to think about what happens if you cross this threshold. Once you cross this virial line mass, there is nothing you can do to stop rapid collapse and fragmentation. And you can clearly see that a lot of our structures do cross this threshold, particularly the massive star-forming regions. And what happens then? Well, your filament rapidly fragments into lots of different cores, and so its structure gets disrupted. Let's think about that in a little bit more detail, because one thing we saw is that this distribution is quite broad, but individual filaments, when we look at their scaling with their own substructure, they lie at different normalization point in this relation. And that's because there are two timescales at line here. We have the accretion from the outside environment onto the filament structure. And this is the time in which the filament can grow in mass and can have its gas replenished, the accretion timescale. And as long as the accretion timescale is shorter than the fragmentation timescale, the filament can survive and even continue to grow in mass. And so this balance between the process of accretion onto filament that forms your filamentary structure and the fragmentation of the filament into individual cores sets the normalization in this mass to length plot. And if we look at our most massive structures, those hubs, we see that these require the highest accretion rates. So looking at this tentatively, this would be about 500 solar masses per parsec per megayear. And again, this fits the data quite well. This is the Musca filament, which has a lower accretion rate, and this Orion, which has a higher. And you can see this balance between the two timescales is different for each of them and consistent with the data. And so we are left with an evolutionary scenario where a filament contains substructure, which always be formed at the time from hierarchical fragmentation or simply be pre-existing within the structure. That this network then accretes and grows, moving it to the right on this plot, until at some point it passes this threshold where the fragmentation time becomes shorter than the accretion time, and you get rapid core formation and growth, which disperses the filament and, of course, triggers lots of feedback from the active star formation in the cores. This happens at different points for different filaments, giving us this broad distribution. And indeed, in simulations, you can see this similar pattern, an evolution of time from left to right, and then mass rapidly moving into cores. And looking at Larson's relations, basically all that I've showed you today is lots of scaling laws. So let's compare them to what Richard Larson found many years ago. And if you look between the two, there is a striking similarity. So have we once again just simply shown that after all this effort, Richard Larson basically solved most of star formation 40 years ago, and he was just too nice a person to rub it into our faces? Possibly. But actually, there are a few subtleties, because the geometry of the gas is different for these filaments. Well, first of all, the Larson objects and the work done subsequently, these structures had a constant column density. But in the filaments, there's a varying column density. But there's also, I think, more interesting implications. So if you combine relations 2 and 3 for a filament, what this means is that this necessitates that the full width half maximum, the length of the filament, has to scale with L, the length, to the power of gamma, which is approximately 1. And that is intriguingly similar to the relation which I showed you earlier in the talk for the nearby filaments. Another thing is that if you combine relations 1 and 2, well, that implies energy balance. But for a filament, it only implies energy balance in the radial direction. Of course, energy balance is not the same as virial equilibrium. It just means that they're of the same magnitude. And so you are free to accrete and move along the filament as much as you want. And putting it all together, this gives us the initial conditions for star formation, where cores form in filaments. The masses is determined by the mass of the filamentary environment which they come from. We have different masses, we have different mass-to-length ratios. This gives us different core masses. That the hubs, that the accretion along these filaments onto cores gives you an additional reservoir which allows you to build up the high mass end of the mass function by subsequent accretion. And that this flow of material onto the cores will affect the evolution of the cores. If we think, the implications for planet formation, these cores are being fed with ongoing material from this filamentary structure. This will become clumpy, it's got substructure. The angular momentum vector of the gas that falls onto the core can be different. This will increase the ability of disks to fragment and affect their evolution. And so filaments connect star-forming cores and disks to the wider interstellar medium, which leads me, once again, to the final conclusions that I showed at the beginning. The interstellar medium is threaded with this network of filamentary structure. It's a continuous hierarchy of structure, of base scaling relations, is formed by many processes, is dynamic in its nature, and is intimately connected with how stars and planets form. Thank you.
Okay, thank you, Rowan. So the chapter is open for questions. So before your question, please state your name and your affiliation. Okay, so let's start from here.
Hi, Mark Krumholz, Australian National University. So I was thinking about how what you said interacts with the talk I gave for the GMC chapter, and it seems like the common theme is that there's no right way to pick out structures, that the properties are simply determined by what contour level you choose to draw or what size pixels you choose to draw in an extragalactic observation, and we should give up on the idea that there are dimensional parameters that characterize anything. Things have certain non-dimensional parameters like virial ratios, which are the same, but what dimensional parameter that maps to depends on the tracer you choose and for fixed tracer on the galactic environment. Would you agree with that statement? And if you would, does that suggest that we should simply not try and characterize stuff as filaments or clouds at all, and we should simply adopt generic ways of characterizing structures, and then we can talk about how filamentary they are by just using something like a semi-major to semi-minor axis ratio?
I think that's an excellent point. And I think that feeds into this point I've been making throughout about hierarchy, in that you're essentially just selecting a different level on the hierarchical structure. One of the things I like about one of the algorithms, which is used to find filaments, FilFinder, is you basically select a scale. It says, I will select filamentary structures on this scale. And then I think that gets to the fact that it depends where you're looking at. And that's due to the hierarchical nature of the interstellar medium. It's almost fractal in the way that this structure is nested within each other. I still think this is a useful way of grouping together structure, that we do learn something about it. But we should maybe move away from thinking of these things as unique objects. Crests in the wave seems like an excellent way of thinking about them to me.
Okay, one more from here.
Maybe related to the previous questions, but there are some clouds that are a bit more sheet-like California. So I was wondering, how would you interpret those clouds in the context of filaments?
Absolutely. You get sheet-like geometries. I think, as we've shown, that gravitational collapse will give you a sheet. And then if you actually look at the sheet-like clouds, and again, this is something you see in simulations, what you find is a network of filaments, which may then lie on a column, a plane. And I think that's very consistent with what we see.
Okay, the front.
Yeah, so Doug Johnstone, National Research Council of Canada. I actually think I disagree with Mark today, which is a first. The thing about a filament is that it's long. It's not a core, it's not a spherical object. And you kept referring to these extended objects, which means they require an environment that has some coherence on a longer scale. And so I was a bit surprised that when you gave all your methods of making filaments, I agree with them, but I was surprised you weren't able to rule things out. Because I would have thought that if I see filaments wrapping along my molecular cloud, then I need a structure that's coherent on that length, and it has to remain for a while.
Yeah, we were surprised too. I think the question is there is a anthropomorphic principle here, in that when you look at these very large structures, they have to have a similar velocity dispersion to be coherent in some scale. And if you think about what is the alternative, well, if these very large structures did have a large gradient, they'd be rapidly torn apart, they wouldn't exist, and you wouldn't see them.
So maybe...
So they do have to have coherence just so you see them. It's a kind of survival of the fittest process.
Okay, so then...
But there are multiple processes that give you that.
Right, but then the question that immediately comes to mind is, can you tell me about the mass as a function of the axial ratio? I think that would be very interesting. How many of these things are long? And is that important? Or are we really just getting back to cores?
But then we get to the point earlier that these are not single objects. So the fibers are not that long. We saw this relation between the length and the mass, and the line mass, and the density. But the fibers are shorter, and then you get things which are longer, but those are superposition of lots of different smaller structures. So again, you have to think of maybe things being swept up in a large scale. It's easy to make something large if you have a galactic process, for example.
Bingo. I think that's really important, because there is a coherence on the large scale, I think. Thanks.
Okay, so the back side.
Adele Plunkett, National Radio Astronomy Observatory in the United States. Thanks, Rowan, for a nice talk. You mentioned how, for a hierarchical structure, it's complicated to define a radius. And then many of your relations are focused on length. For a hierarchical structure, is it also complicated to define a length for the same type of reason?
Yeah, I mean, I think just defining the length and how you segment filaments and where you draw the boundaries is a complex topic. We didn't really have time to talk about filament finding algorithms, but there are a range of approaches which you can use, and in some levels where you segment your filament and call the edges of it will depend on the algorithm used, and it's probably quite important when people do present this data that they also do present some details of how they actually did the identification process. So for example, when you're doing comparison between observations and simulations, you can use the same methodology and make sure you're comparing like with like.
Thank you.
Okay, so there are other people aligning, so please make your question concise and short. Okay, so.
Gilles Chabrier, INS Lyon and University of Exeter. Thank you very much, Rowan, for this remarkable review. I mean, given the number of questions you trigger, you can say it was a very successful talk. So one of the points which are puzzling me is that you stress and you show convincingly that the filaments are constantly evolving. Yet, Philippe André and collaborators define a filament line mass function, which to me suggests that either eventually filaments do reach kind of a steady state, possibly between accretion and fermentation, or that the accretion rate scales linearly with the mass, so m dot over m is constant. Or am I wrong? Or can you comment a little bit on that, please?
I'm not sure about that, to be honest, about the accretion dot radius, the mass scaling. Maybe we should think more about that. What I would say is that the individual substructures are themselves coherent, but it's just that they're moving together with a bulk velocity throughout the region. So in that sense, that explains why they seem to go together, and they can move coherently together until they interact with their surroundings.
Can that lead to a steady state mass function?
I don't know. I think, in my view, it's probably too dynamic to get to that. But I wouldn't say that we have scientific consensus on that. I think that's something we should still be looking at.
Yeah. Thank you.
Okay, so one more from this side, and then.
Philippe André, Paris-Saclay. Thank you very much, Rowan. Very nice talk. I have a question about, you very much emphasize the self-similarity of filamentary structures, but in fact you showed a plot, a velocity dispersion plot, where you had the velocity dispersion versus length, I think.
Yes.
And in this plot, you had a break in the relation. There was a scale, actually. There was a characteristic length. And since you say that length is related to width, I think this also indicates a characteristic width when the filaments are resolved. Could you comment on that?
So I'm just getting the plot.
Yes,
so
this
that
one.
everyone, yeah, I know the one. So yeah, when we look at the smaller scale structure, so these are the fibers. And so these are sonic structures. And so in some way they will be related to the sonic scale. I think the point we would make is that this is not necessarily a constant value, in that there is variation to do with local conditions. But yes, these do have a lower velocity dispersion.
I think it's not only fibers, it's also part of the nearby filaments. There is an overlap between the two.
So if you look here, you can see here in the nearby filaments, and they start to raise. Some of them are lower, but they start to become more supersonic. And so I think you're seeing sort of a mixture. In some nearby filaments, you are seeing something which is a little bit larger than that, maybe goes out a bit wider, maybe includes additional substructure.
Thank you.
Okay, 3 minutes. Okay.
Kei Tanaka, Tokyo Tech from Japan, and thank you very much for a great review. And let me ask about the formation of massive filament. So you mentioned the accretion, some certain accretion rate is needed, but at the same time, to make such massive object, of course, we need more like some time duration, or in other words, total mass. So considering those like accretion rate and also the total mass, what kind of event can be like actual event to form such a massive filament? So I'm asking because, in Japan, many people believe cloud-cloud collision must be the way to form such massive filaments.
So in effect, what you need is a high accretion rate, which makes sense. You need to get together a lot of mass. There are multiple processes which could give you this. So yeah, colliding clouds can do that quite nicely. That can give you an enhancement. You can also, any process which really gathers that mass together, if you have flows within the galaxy. I would agree with what Mark was saying yesterday, in that it's hard to separate them out into individual processes. There are lots of processes happening in the galaxies. We can have expanding shells, we can have material falling into a spiral arm. Anything which brings together a substantial amount of mass should give you this process. And it's hard to give you one individual method. It's just there are lots of flows in the galaxy.
Thanks.
Okay, so 2 more questions, quick questions from backside, and then next.
Yeah, John Tobin, National Radio Astronomy Observatory. At the very end, you got into how filaments impact the cores, and so I was wondering, at what scale, what is the smallest scale that the filaments go down to, and sort of what is the smallest turtle that you're going to find?
Yeah, we kind of purposefully in our review, we didn't go much beyond the core scale, because we wanted to, well, we had to draw a line somewhere, and obviously there's review chapter after us. But yeah, I think you yourself have shown quite nicely that there is filamentary structure even within the core scale. And that makes sense, because if we think about the flow of material that's going on to a disk, it's not coming from all directions. It's flowing on from preferred directions, and even when you're not getting additional accretion onto the core, it inherits that original geometry. I mean, when I've looked at it in simulations myself, you find that the cores are actually almost like little rugby balls. You know, they are prolate. And so that will impact on how it collapses and forms. And so, yeah, I think there can be filamentary structure even within cores.
Thanks.
Okay, so last question.
Hi there, Jennifer Wallace, University of Connecticut. Excellent talk, thank you very much. I just had a quick question, just initial methodology. You gave several categories of filaments at the very beginning of the talk, and I just wanted to know a little, like elaborate a little more, because these are continuous hierarchical structures, as you mentioned, how you sort of settled on those for the meta-analysis, like the definitions that you did end up with. How did you figure out that family of filaments, sort of?
It's more we were kind to look at how filaments had been observationally defined when we were drawing together. So something like an IRDC, infrared dark cloud, that's a purely observational definition. You know, it's a feature which you see in absorption against a bright background, and that can actually, it's very similar to the filaments which we see in galactic surveys. And so this is just trying to draw together the different scales and methods which people observationally have used.
Excellent, thank you.
Okay, thank you so much. So I'm sorry, time is running out, so that please continue the discussion in the Mattermost. So let's thank the Rowan again.